First speaker, I'll go directly to the introduction, is Heiko Kabutz. He's a PhD candidate studying in the animal-inspired movement and robotics lab at the University of Colorado Boulder. He grew up in South Africa and completed his bachelor degree in mechanical engineering from the University of Pretoria in 2019. His research interests include the mechanical design, biomechanics, and insect scale manufacturing of leg movement mechanisms for bio-inspired robotics. With that, I'll let the floor to our speaker. We're very excited to see this talk.
Okay. Yeah, hello. So I'll be presenting on insect-sized robots and how we can have body shape change. In nature, we see organisms actively shape-shifting in constant environments to enhance movement, gain additional functions, and reduce the trade-offs which I have with biomechanics. When we look at different constraints in nature and also human-made systems, we have large multi-environment systems such as open spaces to really constrained environments. And similarly, we also have in our human environments, like open spaces and highly confined machines. But to overcome constraints, in biology, we often see multifunctional systems, which are either body shape change or a claw that can function as multiple different things for different tasks, a beak, a paw, or a hand. And also tools that we designed are often used for more functions than just one. And that's also in robot arms, where robot arm can open the door or pick up something. And the concept is that we see generalist animals sort of all around that are highly adaptable in behavior and also thrive in very diverse environments and conditions, as well as also sometimes these specialist animals with specific environments and a very niche system, where most of it is more in the generalist sense. We see that animals in multi-environment systems can also adapt and perform really well under unexpected disturbances also. This is, for example, a bird flying in rain, or a goat being a goat being able to jump and climb over steep and loose terrain, and also a goat being able to swim and climb over trees that are even in the water, which is not the natural environment of a goat, but it's still really adaptable into these different environments. In addition to being multifunctional in these constraints, a dog using its legs to walk, but also dig a hole, or a crow being able to use its beak from eating, but also using a tool, and a weaver weaving a nest, which is in addition to its main function. And then we see the same also for the body, where the bodies become multifunctional, where a mouse can squeeze through really tight gaps and into a very tight confinement with body compression, or a cat through a very tight space. And this is all with body compliance. And then at the same time, also appendages fold. It's like a wing of a goshawk being able to fold in so that it can navigate through a very tight gap. But on the other side, appendages can also be extended, such as a flying squirrel being able to extend its appendages to increase its flight. And with this, it's sort of proposing that shapeshifting enables systems to locomote under more varying environmental conditions, that changing from one to another enables it to expand that, then enabling new functionalities and thinking bigger than just that one specific task, and reducing the trade-offs that are between the individual features. So in our lab, we've been studying wolf spiders, which are known to be a more generalist spider style, as they appear in a very broad range of environments. And this is a wolf spider running unconfined. And then we've been studying them under confinement, when they run through a very narrow gap. Whereas here we see their body starts oscillating and their appendages, their legs, are rearranged in a very different location or different structure. Similar also with cluttered terrains, where we see with cockroaches, which don't have the appendage moving, but it's more body compliance, that they're really good at climbing, running, diving, and pretty much being indestructible. This is now all of a sudden with the small grass pieces, the cockroach actually being able to climb up even though the grass gives away. And then in addition to this, the cockroaches can run really efficiently in unconfined environments at slight body level, slight confined, and then at 30% of its body height. It's at approximately 90% of its body speed still. So that's under massive compression. And this variation between body compliance and appendage compliance, like plotting a few of these examples, shows us that even with the two very different principles, the animals still perform very efficiently up until quite high levels of body confinement. Yet in the robot world, we sort of have more optimized systems. So most of our robots are designed for specific tasks in a more limited environment. They are highly efficient and very, very good at what they're doing there. And sort of the concept now is more trying to get to generalist robots that are also able to adapt to different tasks in a variety of different environments. This has been especially explored in like soft robotics, where we have soft robots with high degrees of freedom that can now be compliant and move in very different styles of environments and shapes. Yet the highly performing agile robots, which we know, tend to be slightly less adaptable, but have high control over every degree of freedom. That's the robots that now do backflips and all the really fancy control systems we're seeing. And with shape-shifting, it's sort of starting to merge this field of starting to get control into more high degrees of freedom, acknowledging that we're not controlling every aspect of the degree of freedom as a complete soft robot, but adding more degrees of freedom that allows the whole shape to adjust to the most fitting environment around it. Most robots we are currently seeing tend to be more square boxed. So it's a rigid body and we add the appendages. And that does not mean they're bad. They're like, there's been videos as this unitree robot, which are high performing in very extreme environments. And it's still a rigid body, but the appendages move in a very advanced manner. In addition, it's also on the small scale. Like the hammer robot is a micro robot the size of about 2 pennies. And this robot can walk upside down. It can walk in a very dynamic motion. Then this robot is capable of walking or swimming on water and also swimming underwater, like in the whole different terrain environments, and is capable of carrying all its weight, power, electronics, and everything together. This has also led to robot designs that are capable of somewhat body compression, like this cram robot using can walk in unconfined environments and slightly compressed. So this is now a system that's starting to merge these different like exoskeleton ideas in. Plotting these robots on a similar graph of like some robots use body adaptation and others appendage, is that most of the rigid robots perform really high when they're unconstrained. Yet when it becomes more constrained, we see that the soft robots are less agile, but highly adaptable, whereas the rigid robots are the opposite of that. And it's the question of how do we get robots to perform closer to what we see in biology, with the animals still being highly agile and performing even at lower confinements with both the different methods. So we've been exploring in our lab specifically the exoskeleton and shape morphing between different modules and how we can interact a semi-rigid system. There's been a bunch of different robots that have done similar styles of mostly on the wheeled side or flying systems where they have the shape morphing through different modules. And this is a few of those samples. To really push the boundary of this, we sort of in very constrained environments, which tends to be on the small scale. To have a micro robot run or insect in these terrains, it's a lot bigger struggle to cross over rock or leaves or grass than a big robot just stepping over it. So we have significant increase in constraints, which we can then translate into larger robots when we start figuring out these constraints in shape morphing. So for this, we've been building micro robots in the size of a penny. So I've built a bunch of different versions from larger 6-legged to now a really small 4-legged version to advance our progress in shape morphing of designing these micro robots, the manufacturing of it, and how do we incorporate sensing and actuation included in this whole complete package of a robot system, as there's so many different constraints. The manufacturing process we've been using for our tiny robots has been using a stack laminate process where we laser cut joints into individual materials, stack them together and then laminate them into one material piece. And then we release cut them into a system where we can fold some joints, glue them, and actuate other joints into a new complete structure so that we can have an origami system that we manufactured, folded, and move afterwards. For our leg robot systems, it sort of starts with us having a leg design, where this is one cutout of a single leg module, where some joints are folded for gluing and others for actuation. So under a microscope with tweezers, we fold the whole thing together. So that's a very tedious job for us grad students. And then this gets assembled with actuators and a PCB and electronics into individual leg modules, which can then be assembled into a full robot where the leg modules themselves can be arranged in any orientation we want. With this origami structure, we've been using piezoelectric actuators as actuation methods. So we don't have motors running, but it's more the piezoelectric biomorph actuators, which is 2 piezoelectric ceramics, which we also build in-house, and then a carbon fiber layer in the middle. And by applying a sinusoidal like voltage difference, we can get the piezoelectric material to move. So we've been doing a bunch of development on these actuators, where out of approximately 8 millimeter actuator length, we can then get 500 micron in deflection, which is not a significant amount. So the development of our leg systems, that's in our leg module, is very important to actually get this motion working. So we have a carbon fiber rigid base, which connects the whole robot body. And then there's the 2 different actuators, the piezoelectrics, where one controls the swing or the lift, which is then the motion for going up and down, which is directly connected over linkage to the output. And then the other actuator moving the swing, and that's connected via the spherical 5-bar, which gets folded up in the origami system to then move the leg left and right. And through this whole mechanism, we're able to move the leg in any position in the 2D space. So we can move them up, down, left, right, and in any other pattern. So it's not directly vibrating, and we do have control over our motion. With these individual leg models now, depending on how we arrange and assemble them into a module, we can get the robot to start performing in or assume different shapes. So this one is now where if we have joints in between, we can now have the robot compress to its environment, where we've built now clearing, and it's approximately the size of one leg module of a coin. It's a compliant legged articulated robot. And this robot now has 8 degrees of freedom. So every leg being 2 that are actuated, and then it still has a passive body compliance. The whole system is about 2.5 grams, and the piezoelectric actuators need to run at about 225 volt. So it's also quite a power electronics challenge. With all our degrees of freedom that we have actuated, we're able to get the robot to walk in different classical walking gaits. That's also seen with animals and other robots. and then also optimize that for whatever environment the robot is moving in. So this is a classical trot gait. The robot then walking, here it's walking trot, just straight. It might look a slight vibrating, but it's still doing that full leg motion. And then, as this was currently passive, when we glue it into different body shapes, the robot can walk, for example, sideways in a square configuration or narrow. Videos don't seem to be playing very, but that's fine. And then when we unconfine it, we currently had the struggle that there's just so much degree of freedom and the robot doesn't even move at all anymore. So from this first robot system, we sort of had, as expected, the robot performing significantly better when it's in a narrow configuration than when it's wide, but still being capable of walking sideways. And then when we have it untuned, completely unfixed, the robot barely moves at all, as the previous video showed. And then if we start tuning this, we can actually start achieving higher performance again. The challenge with tuning has been also more experimentation, and we ended up developing a new robot system for this. So we built a smaller robot version, which is half the scale of the previous one, and where the whole robot is now the size of a penny, and the individual joints are also more tighter and closer designed with articulation than a human hair. So this robot, the M Clary, which is just the mini Clary, is less than 1 gram and also only 20 millimeters in length. Still using piezoelectrics, but is now capable with the new mechanics, able to carry about 4.5 times its body weight. This robot can, as the previous one, walk in unconfined environments, but also a lot more efficient in omnidirectional, while now not being restricted or fixed in its body shape, but all being passive. And this enables the robot to now passively walk towards a gap and squeeze through it. So there's no active control on the body shape, but it's all passively done to sort of passive body shape morphing. And with the omnidirectionality of the system, it's also able to do the whole thing without turning and compressing in a different direction. So now the robot squeezes in the one direction and then without turning, moves downwards again. Sort of enabling new capabilities which without shape morphing weren't really possible before. So on the graph now, the M-Clay robot doesn't significantly improve what we've seen with other robots do, but it's sort of a new approach to bringing us hopefully closer to what we've been seeing with the animals and starting to merge these fields a bit. So to find new approaches on how to approach this robot now, we've been building living hinge systems where we've been building joints to improve the body shape so that we can have smarter body origami linkages in our system. And then also starting to include how do we add sensing into these robots better, as most of them had been open loop. So I've been developing more closed loop sensing actuators, which is similar to an encoder in your normal moving motor, where we have the piezoelectric materials and now add a polymer PVDF piezoelectric layer on top of it, which then allows us to independently measure the actuation, which is uncoupled from the already rest of the actuator. This provides a bunch of mechanical machining challenges, but then provides us with the capability of closed looping and measuring the deflection of our robot actuators. So we know exactly where the actuator is, as well as we can measure the force of how much force is now going through the actuator. This has allowed us to build leg modules now, where the robot leg itself can start detecting rough surfaces around it and start measuring the environment conditions. Like how does the shape morphing interact with the changing conditions? And then the main next step had been, we want to get this active shape change. The previous two examples of the robot were all passive. How do we get the robot to now actively shape change? So we've been doing a bunch of development on trying different styles of actuation So this is more a liquid-based electrostatic Hazel actuation style, where now the robot can start changing shape. So this is a more lower deflections, but based on actuation, the robot can reorientate its legs in different directions and change its width. And this enables us with new capabilities. For example, in this video, that the robot is carrying an electrical piece and then dropping it off at a circuit. And by dropping it off, it creates a connection, starting the LED, and then with a change shape, can move away again. So this is now using the shape change as a function, as a tool and chain manipulating the environment instead of just trying to squeeze through the environment. And with this shape adaptation, sort of the next steps now are really trying to further research, how do animals actually do this? Is it more just a passive compliance, or how active do they really change it and adapt? And then how do robots in future, how can we increase that by actively changing and intentionally changing the shape into creating these new systems towards adapting their environments? And the vision sort of next has now been that we really want to use shape-shifting robots that are capable of high performance, multimodal locomotion, and also use it as a multifunctional, so that it's enabling the behaviors more into real world and not just a live environment. And with that, it's sort of been the next open question we've been working with, even with the last few things I've been showing, of how do we understand what shape really is of the robots? How can we sense it, that we improve our sensing and incorporation of these robots? And what's even the most optimal shape finding? Are there specific shapes that tend to be working better in specific environments? With that, I want to thank everyone else from my lab and my advisor, Kaushik Jairam, and the funding sources. Thank you.
Thank you very much. So I'll clap for all of our attendees who can't do that since they don't have their image. And we'll go ahead with the question and answer. There's a couple of questions in the Q&A feature right now. If any other attendees have questions, please feel free to ask them. I'll start with the first one. This one came early into your talk, so you might have answered it already, but just in case, I'll ask it again. So Rishi Raj asks, what do you mean by biomechanical trade-offs? And are you trying to offset certain disadvantages in design?
So with biomechanical trade-offs, we're specifically more mentioning in the direction of we see in nature that there's one device not necessarily just doing one thing, as we see like in car manufacturing, where one robot does one specific task, but to have a system that can now walk, swim, that can, in biology, also heal itself, it grows, and all of that, but in one really well-working system together. Every one of the individual parts, for example, actuation, we could build an actuator like a muscle that's more powerful, but it comes with a trade-off that we might not be able to do many of the other features. And that's been, for example, the struggle we're having with our actuators. We have a high force, low deflection, but they're still rigid. And that's sort of one of these trade-offs. How can we build actuators that are now also maybe soft? And we might lose some of the force out of it, but gaining the capability of having softer and maybe self-healing actuators. And that's sort of one of these trade-offs.
Perfect, thank you. And then a second question that asks whether these sub-robot designs kind of defeat the purpose of bioinspiration, since animals are able to achieve these locomotions using advanced bone structure and muscle actuation. So does it make sense to build such complicated piezoelectric systems to imitate sort of straightforward natural motion? I think that
I'm a bit confused with that question.
Could you repeat the question? They're trying to understand, since we have bones and muscle structures that seem like a simpler design than what you're trying to do here. Does your more complex
Okay.
design sort of defeat the purpose of it.
Okay. Yeah, that makes very much sense on the question that where it depends on the scale we're looking at. So if we're looking at a larger scale like mammals, most of it is a more internal skeleton. And that's also the approach many other robots have been using. When we look at the scale of insects, where we've been looking at, all of them are exoskeletons. So everything is inside, and we actually have a body that's compliant and shape changing. So it's all the mechanics needs to be inside, and the body itself starts taking a more crucial role. So I would say that's sort of the big difference in, it depends on what bioinspiration system you also start looking at. And when we look at the small scale, we see a significant amount of exoskeleton where the body is just highly connected with all the actuation and system.
Thank you. Hopefully that answered the participant's question. I did have more sort of specific questions about your system. You have this very complex sort of 5 linkage leg. How did you come up with this design? Is it imitating nature in some way, or did you do some sort of optimization on it? How did you end up on that design?
So the base spherical 5-bar system was first invented for the hammer robot, which has been showing all the highly capable, more rigid body locomotion that wasn't done by Harvard and that whole system. So that's the base concept of a mechanical 5-bar linkage. And it's directly just connecting the individual pieces. And then most of our optimization has been on optimizing the performance of it, the like linkage lengths. So that's been slide simulation, a lot of mechanical design optimization, and then also incorporating the actuation into a leg module. So splitting it from actuation in a body to actuation per leg on the micro scale, which on the large scale, we see everyone pretty much always has a motor exactly at where they want. On the small scale, that's not really been possible.
I see. And then sort of following up on that, but in the case where you have sensing capabilities, are you planning to sort of change your gait as a function of what your surface looks like to maybe slide less if it's a very slippery surface? What sort of feedback are you thinking about, and how do these leg shapes in particular help with that feedback?
Yes. So the sensing specifically on the leg, at this point, what I showed here was sensing on the actuator, which is sort of enabling us to know what's actually the force, or what's the performance we are getting out of what we're putting in. That's the first step of closed loop. We've also been developing systems at the joints at the output so that we have full sensing of what our actual robot does, which is a bit more common on the larger scale, but not on a small scale. And that's enabling us specifically, as you mentioned, different surface interaction and detection. Like if it's a rough surface and the robot is slipping, accommodating for it. If a leg gets stuck, to actually make it a more ensured closed loop, full performance of a leg module, that a leg doesn't skip half a beat or so.
Thank you. Yeah, it's very exciting research. We have maybe 1 minute if anyone has a very last question. Okay, I think we answered most of our questions. So we'll thank our speaker again. Thank you for this very exciting talk.